Hello, everybody. This is the third day of our crash course, and we're going to learn transformer architectures and their key components. Transformers, first introduced in 2017, revolutionized AI, particularly in NLP. Prior to transformers, models like RNNs and LSTMs were used to handle sequential data such as language. However, these models struggled with capturing long-range dependencies due to their sequential processing. In contrast, transformers use a self-attention mechanism, which allows them to process all tokens in parallel, significantly speeding up training and improving performance. The introduction of transformers also enabled better handling of long-range dependencies in sequences. These advantages have made transformers the core architecture for modern NLP models, with models like GPT, BERT, and T5 achieving state-of-the-art results in tasks such as language generation, translation, and summarization. Their success has extended beyond NLP to fields like computer vision and reinforcement learning, setting new benchmarks in a variety of AI tasks. Before transformers, RNNs and LSTMs were the dominant models for sequence tasks. These models processed data one token at a time, which made training slow and inefficient, especially for long sequences. RNNs suffered from issues like vanishing gradients, which made them less effective at handling long-range dependencies. LSTMs improved upon this by introducing memory cells, but they still struggled with sequential processing. The attention mechanism emerged as a breakthrough that allowed models to focus on the most relevant parts of the sequence, no matter their distance from the current token. This mechanism also allowed for parallelization, a critical innovation that made it possible to process entire sequences simultaneously. The development of transformers built on this attention mechanism, offering even more parallelism and scalability, which dramatically improved training efficiency and model performance. This leap forward laid the foundation for the powerful transformer-based models that dominate the AI landscape today. The transformer model is organized into two main components, the encoder and the decoder. Both parts are composed of multiple identical layers. The encoder takes in the input sequence, processes it through its layers, and generates dense representations of the sequence. The decoder then uses these representations to generate the output sequence. Each layer of both the encoder and decoder consists of a self-attention mechanism and a feed-forward neural network. The self-attention mechanism allows the model to focus on different parts of the input sequence, while the feed-forward neural network refines the representations. Since transformers process all tokens in parallel, they need a way to account for the order of tokens in the sequence. This is achieved through positional encoding, which is added to the token embeddings to provide information about the position of each token. These combined elements enable transformers to efficiently handle long-range dependencies in data and learn complex relationships between tokens. Self-attention is a key mechanism that allows transformers to handle long-range dependencies and parallelize computation. Each token in the input sequence is represented by three vectors, a query, a key, and a value. The query of one token is compared with the keys of all other tokens in the sequence to calculate similarity scores, which are then used to assign attention weights. These weights indicate how much focus each token should have on the other tokens. The attention weights are used to compute a weighted sum of the value vectors, which produces the output for the current token. The scaling factor, which divides the dot product by the square root of the key dimension, ensures the attention scores remain stable during training. To enhance the model's capacity to capture diverse relationships, transformers use multi-head attention. This involves running several attention mechanisms in parallel, each with different sets of query, key, and value projections. The outputs from these multiple heads are concatenated and linearly transformed to form the final result. Transformers process input tokens in parallel, so they lack the inherent ability to understand token order. However, for tasks like language translation or text generation, the order of tokens is crucial to capturing the meaning of the sequence. To address this, positional encoding is introduced. The original transformer model uses sinusoidal functions to generate a unique encoding for each position in the sequence. The sinusoidal encoding ensures that each position is assigned a distinct vector that can be easily distinguished by the model. These positional encodings are added to the token embeddings before they are passed through the network. This addition allows the transformer to maintain sequence information while still benefiting from the efficiency of parallel processing. The inclusion of positional encoding is essential for tasks that require a clear understanding of token order, as it enables the model to preserve the structure of the sequence and make accurate predictions or generate coherent sequences. In transformers, feed-forward neural networks, FFNs, play an important role in processing the output from the self-attention mechanism. Each transformer layer includes a position-wise FFN, meaning the same network is applied to each token independently. The FFN consists of two fully connected layers with a ReLU activation function in between. The first layer increases the dimensionality, while the second reduces it back to the original size. This nonlinearity introduced by the ReLU activation allows the model to capture complex patterns and relationships within the data. After the FFN, layer normalization is applied to stabilize the learning process and ensure consistent activations. Layer normalization helps to prevent issues like vanishing or exploding gradients by normalizing the activations across each token. This combination of FFNs and layer normalization allows the transformer to refine its token representations and learn more intricate features of the data, contributing to the model's overall performance. The transformer architecture consists of stacked encoder and decoder layers, each containing identical sublayers. The encoder processes the input sequence and generates a set of high-level representations. The decoder then uses these representations to generate the output sequence. The encoder consists of self-attention layers and feed-forward neural networks, allowing it to learn contextual relationships in the input data. The decoder has a similar structure but includes an additional cross-attention layer, which enables it to attend to the encoder's output. This cross-attention mechanism is crucial for tasks like machine translation, where the output sequence must be directly aligned with the input sequence. Each encoder layer helps build a richer representation of the input, which the decoder can then use to generate accurate output sequences. This stacked architecture enables the model to handle increasingly complex tasks by processing the input in multiple stages and refining the representations at each layer. In the transformer decoder, self-attention operates similarly to the encoder's self-attention, but with one crucial difference: the decoder attends only to the tokens that have already been generated. This prevents the model from peeking into future tokens during generation. Additionally, the decoder includes cross-attention layers that allow it to attend to the encoder's output. The cross-attention mechanism enables the decoder to focus on relevant portions of the input sequence while generating the output, which is especially important in tasks like machine translation, where each token in the output sequence depends on various tokens in the input sequence. By combining both self-attention and cross-attention, the transformer model can efficiently generate sequences that are well aligned with their input context, ensuring that the generated outputs maintain coherence with the input data. During training, the transformer decoder employs a technique called masking. This masking ensures that each token in the sequence only has access to tokens that precede it, preventing information leakage from future tokens. This is crucial for tasks like text generation, where each token generated depends on the tokens before it, and not the ones that come after. The model is trained to predict the next token in an autoregressive manner, meaning it generates one token at a time, conditioned on the previous tokens. The masking ensures that the model generates sequences in the correct order by ensuring that the decoder does not have access to future information during training. This technique allows the transformer to generate coherent and accurate output sequences in tasks such as language modeling or machine translation. Multi-head attention is a crucial feature of the transformer model. Instead of having a single attention mechanism, the model uses multiple attention heads that run in parallel. Each head learns to focus on different aspects of the input sequence, capturing various types of dependencies. For instance, one head might focus on short-range dependencies, while another could capture long-range relationships between tokens. By running multiple attention mechanisms simultaneously, the model can capture a richer set of features from the input sequence. The outputs from all attention heads are concatenated and passed through a linear transformation to produce the final attention output. This enables the transformer to learn from multiple perspectives and improve its performance in understanding complex relationships within the data. Multi-head attention is one of the reasons transformers are so effective for tasks requiring deep contextual understanding. Layer normalization is an essential technique used in transformers to stabilize training. It normalizes the activations of each token's representation across the feature dimension, ensuring that the output of each layer has a mean of 0 and a standard deviation of 1. This helps reduce the internal covariate shift, where the distribution of activations changes during training, which can slow down convergence and make training less stable. Unlike batch normalization, which normalizes across a batch of data, layer normalization operates independently on each token, making it more suitable for sequential data processing. By applying layer normalization after the self-attention and feed-forward layers, transformers are able to maintain stable activations, resulting in faster training and more reliable model performance. Training transformers effectively requires large datasets and significant computational resources. Since transformers have a vast number of parameters, they are highly data hungry, needing large amounts of labeled data to learn meaningful patterns. The training process typically uses gradient descent and backpropagation to minimize the loss function, adjusting the model's parameters over many iterations. However, the sheer scale of transformers with billions of parameters makes training them a challenging task, especially without sufficient data or compute power. To overcome this, researchers have turned to transfer learning, where a pre-trained transformer model is fine-tuned on a specific task using a smaller dataset. This allows models to leverage the general knowledge they've acquired during pre-training, significantly reducing the need for large task-specific datasets and speeding up the training process. Fine-tuning also helps improve model performance on specialized tasks like question answering, summarization, or sentiment analysis. Transformers have been highly successful across a wide range of NLP tasks, fundamentally changing how models are built for tasks like text classification, named entity recognition, NER, and question answering. For text classification, transformers like BERT use their bidirectional attention to capture the full context of the input text, leading to superior performance over traditional models. In NR, transformers can identify and classify entities like names, dates, and locations by using their attention mechanisms to focus on the most relevant parts of the text. For question answering, transformers have achieved state-of-the-art results by reading and understanding the context of a passage and generating an accurate answer based on that information. In language generation tasks, transformers like GPT excel at generating coherent and contextually relevant text by leveraging their autoregressive capabilities. Transformers' versatility has made them the go-to architecture for modern NLP applications, setting new performance benchmarks in each of these areas. While transformers were initially designed for NLP, they have also shown great promise in computer vision. Vision transformers, VIT, adopt the transformer architecture to handle image data by treating an image as a sequence of patches. These patches are flattened and linearly embedded, just like tokens in NLP tasks, and pass through a transformer model for feature extraction. This approach has been shown to outperform traditional convolutional neural networks, CNNs, on large datasets, as transformers are better at capturing long-range dependencies and global context, which is crucial for vision tasks. While CNNs excel at capturing local features through convolutions, transformers can capture global patterns, enabling them to learn more complex relationships within the image. Scaling transformers for vision tasks requires large amounts of labeled data and computational power, but the results have demonstrated that transformers can achieve state-of-the-art performance on image classification, object detection, and segmentation tasks. Transformers have proven to be effective for time series forecasting, where the task is to predict future values based on past observations. Unlike traditional methods like ARIMA or LSTMs, transformers excel at capturing long-range dependencies, which is crucial when the relationships in the data are not just local, but span over extended time periods. The self-attention mechanism in transformers allows the model to focus on relevant parts of the input sequence, regardless of their position in time, making it especially useful for handling nonlinear and complex patterns in time series data. Additionally, the parallelism provided by transformers enables faster training, which is a major advantage when working with large time series datasets. By incorporating positional encoding, transformers can also preserve the temporal order of data while processing it efficiently, making them highly effective for forecasting tasks across various domains such as finance, healthcare, and energy. Despite their impressive performance, transformers come with several challenges that can make them difficult to deploy in certain environments. One of the most significant challenges is their high computational cost, both in terms of memory usage and processing power. The self-attention mechanism scales quadratically with the sequence length, meaning that longer sequences require exponentially more computation and memory. This can be a barrier when dealing with large datasets or working in resource-constrained settings. Additionally, transformers are highly data-hungry, requiring large amounts of labeled data to train effectively. Without enough data, they are prone to overfitting, where the model learns to memorize the training data rather than generalizing to unseen examples. Another challenge is their limited interpretability. While transformers can achieve state-of-the-art performance, understanding why they make certain predictions is difficult. This lack of transparency is a concern in applications where interpretability is crucial, such as healthcare or legal systems. To address the computational challenges of transformers, researchers have proposed several efficient transformer variants. One approach is to reduce the attention complexity, as the original transformer self-attention mechanism scales quadratically with the sequence length. Variants like reformer and linformer aim to reduce this complexity by approximating the attention mechanism or using sparse attention patterns, which make it feasible to process longer sequences more efficiently. Additionally, memory optimization techniques, such as attention pruning or low-rank approximations, can help reduce the memory footprint of transformers. Hybrid models, which combine transformers with other architectures like CNNs or RNNs, are also being explored to leverage the strengths of different types of models. These hybrid models aim to improve both computational efficiency and performance, making transformers more accessible for a wider range of applications. Transfer learning has been a game changer in the field of deep learning, and transformers have greatly benefited from this approach. With transfer learning, models are pre-trained on large, general-purpose datasets, allowing them to learn universal features that can be adapted to a wide range of tasks. After pre-training, these models are fine-tuned on task-specific data, allowing them to learn the particular nuances of the task at hand. This approach drastically reduces the need for large labeled datasets for each individual task, which has made transformers more accessible. Popular pre-trained models like BERT and GPT have been fine-tuned for a variety of tasks, including sentiment analysis, machine translation, and question answering. The flexibility of transformers in transfer learning has allowed them to dominate a wide array of NLP tasks with minimal additional training, setting new benchmarks in almost every major NLP competition. Multimodal AI, which combines different types of data such as text, images, and sound, has seen significant advancements through transformers. By using cross-modal attention mechanisms, transformers can learn relationships between different types of data, making them effective for tasks that require understanding multiple modalities. For example, in vision language tasks like image captioning or visual question answering, transformers can combine information from both text and images to generate coherent responses or descriptions. Models like CLIP, contrastive language image pre-training, and DAL-E have demonstrated the power of transformers in understanding and generating content across multiple modalities. The ability to integrate various data sources opens up new possibilities for AI, from improving accessibility, e.g., audio descriptions for images, to enabling more natural human-computer interactions. In the future, transformers are likely to play a central role in the development of more integrated AI systems that can seamlessly process and understand diverse forms of data. Transformers have become the backbone of many real-world AI applications, particularly in the realm of NLP. Machine translation systems like Google Translate have been transformed by the introduction of transformer models, which now provide more accurate translations by capturing complex dependencies between languages. In language modeling, models like GPT-3 have demonstrated impressive capabilities in text generation, enabling tasks ranging from writing coherent essays to answering questions. BERT has revolutionized question answering systems by providing bidirectional context, allowing for more accurate understanding of both the query and the surrounding text. Beyond text, transformers are also being applied in speech recognition and synthesis, where models like Wave2Vec and Tachytron leverage the same transformer architecture to generate high-quality transcriptions and natural-sounding speech. These applications demonstrate how transformers are reshaping AI across industries, from improving translation services to enabling more advanced virtual assistants. Transformers have significantly improved text summarization tasks, particularly in abstractive summarization, where the goal is to generate a concise summary that maintains the core meaning of the original text. Unlike extractive summarization, which involves selecting key sentences directly from the input, abstractive summarization generates new sentences. This is where transformers excel, thanks to their ability to understand and generate fluent text. Models like BART, bidirectional and autoregressive transformers, and T5, text-to-text transfer transformer, have been fine-tuned for summarization tasks, leveraging both encoder-decoder architectures. These models are capable of producing summaries that are not only concise, but also coherent and contextually accurate. By learning to rewrite the input in a more digestible form, transformers can generate summaries that provide a clearer understanding of the original content, which is valuable for applications like news aggregation and legal document analysis. Fine-tuning and hyperparameter optimization play a critical role in the effectiveness of transformer models. The hyperparameters, such as learning rate, batch size, and number of attention heads, significantly influence the model's performance. Grid search and random search are common techniques for exploring the hyperparameter space, but more advanced approaches like Bayesian optimization or reinforcement learning are also gaining traction for finding optimal configurations. One key hyperparameter is the learning rate, which often requires careful tuning. Learning rate schedulers can help by gradually adjusting the learning rate during training, preventing overshooting of the optimal solution. Fine-tuning a pre-trained transformer on task-specific data allows the model to adapt its general knowledge to the nuances of the task, leading to significant improvements in accuracy. Fine-tuning with the right set of hyperparameters can transform a model from good to state-of-the-art, making it crucial for achieving top-tier results in real-world applications. Transformers, unlike recurrent neural networks, RNNs, or convolutional neural networks, CNNs, do not inherently process sequential data in a way that respects the order of tokens. Therefore, positional encoding is introduced to provide information about the relative or absolute position of tokens in the sequence. Two main types of positional encoding exist: absolute and relative. Absolute positional encoding encodes the position of each token in the sequence, while relative positional encoding encodes the distance between tokens. Sinusoidal positional encoding, introduced in the original transformer paper, uses sine and cosine functions to create unique vectors for each position, ensuring that each token can be distinguished by its position in the sequence. Another approach is learned positional encoding, where the model learns the optimal encoding during training. This helps transformers understand the order of words, which is crucial for tasks like translation or text generation, where the meaning of a sequence can change dramatically depending on the order of tokens. Self-attention and cross-attention are two key components of the transformer architecture, each with distinct roles in the process of sequence understanding and generation. Self-attention allows each token in a sequence to attend to every other token in the sequence, capturing complex dependencies between words regardless of their position. This mechanism is fundamental in the encoder, where the model needs to build a rich representation of the input sequence. On the other hand, cross-attention occurs in the decoder, where each token generated by the model attends to both the previously generated tokens, self-attention, and the encoder's output, cross-attention. Cross-attention enables the decoder to focus on relevant parts of the input sequence while generating the output sequence, making it essential for tasks like machine translation, where the output must be closely aligned with the input. By incorporating both types of attention, transformers can effectively understand and generate complex sequences, leading to their success in a wide range of applications. Handling long sequences is one of the significant challenges faced by transformer models. While transformers are great at capturing long-range dependencies due to their self-attention mechanism, this very mechanism comes with a quadratic time complexity, making it computationally expensive as sequence length increases. For example, if the sequence length is doubled, the computational cost increases fourfold, which becomes a bottleneck when processing long documents or large datasets. To address this issue, several strategies have been proposed. Sparse attention methods, such as the longformer, use a fixed attention pattern where each token only attends to a small subset of other tokens, reducing the computational burden. Another approach is linear attention, which aims to approximate self-attention to bring its complexity closer to linear, allowing transformers to scale more efficiently. However, these solutions often come with trade-offs, such as reduced expressiveness or the need for careful tuning. The introduction of transformers has had a profound impact on AI research, particularly in the field of natural language processing, NLP. Transformers have not only set new performance benchmarks in a wide range of tasks, such as text generation, translation, and summarization, but have also paved the way for the rise of large pre-trained models. The success of models like BERT, GPT, and T5 has revolutionized the way AI models are trained and deployed, emphasizing the power of transfer learning. Researchers now train massive models on large corpora of data and then fine-tune them for specific tasks, significantly reducing the amount of task-specific data required. This has led to significant improvements in model performance and efficiency. Moreover, The transformer architecture has extended beyond NLP into areas like computer vision, time series forecasting, and even multimodal AI, further cementing its place as a foundational architecture in modern AI research. The transformer revolution has reshaped the landscape of AI development, driving innovation and accelerating advancements across various domains. Looking to the future, there are several exciting directions in which transformer models are likely to evolve. One major area of focus is improving the efficiency of transformers, particularly in terms of reducing their computational cost and memory requirements. Researchers are continuing to explore more efficient transformer variants, such as sparse and linear attention, to allow these models to scale more effectively. Another promising direction is the integration of transformers with other AI models, such as reinforcement learning, to create more sophisticated systems that can learn from both structured and unstructured data. Advances in unsupervised learning, where models learn from unlabeled data, could also lead to more powerful transformer models that require less labeled data for fine-tuning. Finally, real-time applications, such as chatbots or live translation systems, could benefit from further optimizations to improve the speed and responsiveness of transformer models. The future of transformers is filled with opportunities, and ongoing research will continue to drive innovation and push the boundaries of what's possible with AI. Transformers are being increasingly explored in reinforcement learning, RL, where the goal is to learn decision-making policies by interacting with an environment. Traditionally, RL has relied on recurrent architectures like LSTMs to handle sequential dependencies. However, transformers bring significant advantages, particularly in handling long-term memory and planning. Their self-attention mechanism allows them to consider long-range dependencies more effectively, which is useful in decision-making tasks requiring long-term strategy. Models like DeepMind's Godot and Decision Transformer have demonstrated how transformers can be used in RL by treating reinforcement learning as a sequence modeling problem, where past experiences are encoded as input sequences. However, challenges remain. RL typically requires extensive exploration, and the computational demands of transformers can make training inefficient. Transformers are making a significant impact in healthcare by improving various AI-driven applications. In medical text processing, transformers help analyze clinical notes, summarize patient histories, and extract important information from unstructured medical records. This can greatly assist healthcare professionals in making informed decisions. In drug discovery, transformers are used to predict chemical interactions and assist in designing new drugs. A groundbreaking application of transformers in healthcare is protein structure prediction, where DeepMind's AlphaFold has revolutionized the field by accurately predicting protein folding patterns, a task critical to understanding diseases and developing treatments. However, challenges remain in deploying transformers in healthcare, including data privacy concerns and the interpretability of model decisions. Since medical decisions can have life or death consequences, understanding why a model makes a certain prediction is crucial for trust and adoption in clinical settings. While transformers were originally designed for NLP, they have recently gained traction in computer vision with the introduction of vision transformers, VITs. Unlike convolutional neural networks, CNNs, which use local receptive fields, VITs process an image as a sequence of patches and apply self-attention mechanisms to learn relationships across the entire image. This global receptive field gives transformers an advantage in capturing long-range dependencies in images. VITs have achieved state-of-the-art performance in tasks like image classification and object detection, surpassing CNNs in certain benchmarks. However, transformers in vision face challenges such as high computational cost and the need for large-scale training data. Researchers are actively working on making VITs more efficient by developing hybrid models that combine CNNs with transformers or introducing sparse attention mechanisms to reduce computational overhead. Transformers are transforming speech processing tasks, enabling advancements in both automatic speech recognition, ASR, and text-to-speech, TTS, synthesis. In ASR, models like Wave2 Vec 2.0 use self-supervised learning to process raw audio signals, eliminating the need for extensive labeled data. This allows speech recognition models to generalize better across different languages and dialects. In TTS, transformer-based models like Tachytron and VTS generate natural-sounding speech with improved prosody and intonation. OpenAI's Whisper model is another breakthrough, demonstrating strong multilingual ASR capabilities. One of the major advantages of transformers in speech processing is their ability to handle long-range dependencies in audio data, resulting in more accurate transcriptions and natural speech synthesis. However, challenges such as computational complexity and real-time processing limitations remain areas of active research. Transformers are powerful but computationally expensive, making it difficult to deploy them on resource-constrained devices such as smartphones, IT devices, and embedded systems. To address this, researchers have developed model compression techniques like quantization, pruning, and distillation. Quantization reduces the precision of model weights, lowering memory and compute requirements. Pruning removes less important model parameters, reducing complexity while maintaining performance. Distillation involves training a smaller, student, model to mimic a larger, teacher model, as seen in MobileBERT and TinyBERT. These optimizations enable transformers to run on edge devices with limited power and memory. However, there is always a trade-off. Reducing model size too aggressively can lead to decreased accuracy. Finding the right balance between efficiency and performance is an ongoing challenge in deploying transformers at scale. As transformers become more powerful, ethical concerns surrounding their use are becoming increasingly important. One major issue is bias in language models. Since transformers learn from vast amounts of internet data, they can inherit and amplify existing biases present in the data. This can lead to unfair or discriminatory AI outputs, particularly in applications like hiring, policing, and loan approvals. Another concern is the potential for transformers to generate misinformation and fake content, making it difficult to distinguish real from artificial information. Privacy concerns are also prominent, especially when transformers are used in sensitive domains like healthcare and finance. To mitigate these risks, researchers are developing methods such as dataset filtering, fairness-aware training algorithms, and transparency tools to audit model behavior. Ensuring ethical and responsible AI deployment is a crucial challenge for the future of transformers. GPT-4 represents one of the most advanced transformer-based language models to date, building on the foundations laid by GPT-3. Its architecture remains largely similar, using a large-scale decoder-only transformer model, but it features enhancements in areas such as reasoning, factual accuracy, and reduced bias. One key improvement in GPT-4 is its ability to follow nuanced instructions and generate more coherent and contextually relevant responses. GPT-4 has been widely adopted in applications such as chatbots, content creation, and programming assistants. Despite these advancements, limitations remain. GPT-4, like its predecessors, still struggles with hallucinations, generating plausible but incorrect information, and can require enormous computational resources. Ongoing research aims to refine such models by improving factual grounding and making them more efficient. While transformers have revolutionized AI, researchers are already exploring what might come next. Several alternative architectures, such as state space models, SSMs, like Mamba, are being developed to address the inefficiencies of transformers, particularly in long-sequence processing. These models aim to provide the benefits of transformers while reducing computational overhead. Hybrid models that combine transformers with other techniques, such as graph neural networks or reinforcement learning, are also emerging to tackle complex AI problems. Additionally, transformers are expected to play a key role in the development of artificial general intelligence, AGI, where AI systems can learn and reason across multiple domains. The future of AI is likely to involve continuous evolution, where transformers remain a foundational technology but are enhanced or replaced by more efficient architectures. Multimodal models aim to process and integrate multiple types of data, such as text, images, and audio, within a single AI system. Transformers have significantly advanced multimodal learning by enabling cross-modal interactions. OpenAI's CLIP, contrastive language image pre-training, can understand images in the context of text descriptions, while DALL-E generates images from textual prompts. Another example is Flamingo, which allows seamless interaction between text and images for vision language tasks. These models have broad applications, including image captioning, visual question answering, and generative AI. However, challenges remain, such as aligning different data modalities effectively and handling the increased computational complexity. Future research focuses on making these models more efficient and adaptable, allowing them to generalize better across different types of input. The financial industry has embraced transformers for a variety of applications, leveraging their ability to process vast amounts of text and numerical data. In algorithmic trading, transformers analyze market trends and execute trades based on real-time information. Financial sentiment analysis uses transformer models to extract insights from news articles, social media, and reports to predict market movements. Additionally, fraud detection benefits from transformers' ability to identify patterns in large datasets, improving anomaly detection systems for identifying suspicious transactions. However, applying AI in finance also presents challenges. Regulatory compliance, ethical considerations, and model interpretability are critical issues. Financial institutions are actively working on explainable AI techniques to ensure these models are transparent and align with industry regulations. One of the biggest challenges with transformer models is their lack of interpretability. Unlike traditional machine learning models, transformers function as complex, black boxes, making it difficult to understand how they arrive at decisions. Researchers have developed various techniques to improve explainability, such as attention visualization, which highlights which words or tokens a model focuses on when making predictions. Other methods, like SHAP, Shapley additive explanations, and LIME, local interpretable model-agnostic explanations, help break down the contribution of individual features in a model's decision. Explainability is crucial in high-stakes applications, such as healthcare and finance, where understanding why a model made a specific prediction is essential for trust and accountability. Ongoing research aims to enhance interpretability without compromising model performance. Continual learning allows AI models to learn from new data over time without forgetting previously learned information. Traditional deep learning models, including transformers, suffer from catastrophic forgetting when new knowledge overwrites old knowledge, leading to a decline in previously learned skills. Techniques like elastic weight consolidation, EWC, help by selectively preserving important weights to prevent forgetting. Another method, replay memory, involves periodically retraining the model on past data. Continual learning is particularly valuable in real-world applications, such as personalized AI assistants, fraud detection systems, and adaptive recommendation engines. Research is ongoing to make transformers more adaptable to changing environments while minimizing the risk of forgetting. Transformers are increasingly being used in robotics to improve perception, planning, and control. Unlike traditional rule-based approaches, transformer-based models can learn from multimodal sensor data, such as camera feeds, LiDAR, and proprioceptive signals. This allows robots to make better decisions in dynamic environments. One application is autonomous navigation, where transformers process sequences of observations to predict the optimal path. Additionally, reinforcement learning combined with transformers can improve robotic decision-making. However, challenges remain, particularly in terms of latency. Transformers are computationally intensive, making real-time processing difficult. Researchers are exploring ways to optimize transformers for low-latency applications, making them more suitable for real-world robotic systems. Training large-scale transformer models requires enormous computational resources, making optimization a key focus area. One strategy is distributed training, where computation is split across multiple GPUs or TPUs to speed up training. Model parallelism divides the model itself across different hardware units, while data parallelism distributes data batches across multiple processors. Techniques like mixed precision training and gradient checkpointing help reduce memory usage without sacrificing accuracy. Advances in hardware acceleration, including specialized AI chips like TPUs and NPUs, further enhance efficiency. These optimizations are crucial as transformer models continue to scale, allowing researchers to train larger and more powerful AI systems without prohibitive costs. Given the computational demands of traditional transformers, researchers have developed several efficient variants. Sparse transformers reduce the number of attention calculations, making them more scalable. Linformer and Performer use approximations to make self-attention computations linear in complexity instead of quadratic. Longformer and BigBird enable transformers to handle longer sequences efficiently by introducing local and global attention mechanisms. Each of these variants comes with trade-offs. While they improve efficiency, some may slightly reduce expressiveness or require additional tuning. As transformers are deployed in more real-time applications, efficiency improvements will remain a critical research area. Transformers have revolutionized generative AI by enabling models to produce highly realistic text, images, and even music. In text generation, models like GPT-4 have set new standards for coherence and creativity. Text-to-image models like DALL-E and Stable Diffusion allow users to create detailed images from simple text prompts, while text-to-video generation is an emerging field with promising results. In the music industry, transformer-based models can compose original melodies and generate audio content. However, the rise of generative AI also brings ethical challenges, such as deepfake technology, misinformation, and copyright concerns. As these models become more advanced, researchers must develop safeguards to prevent misuse. As transformer models improve, they are reshaping how humans interact with AI. Conversational AI is becoming more natural and responsive, with models like ChatGPT enabling fluid dialogue. AI is also increasingly being used as a creative collaborator, assisting with writing, coding, and design tasks. Personalization is another key trend. AI systems powered by transformers can tailor responses and recommendations based on user preferences. However, with increasing automation, there is a need to ensure human control over AI-generated content. The challenge lies in striking a balance between AI assistance and human decision-making, ensuring that AI remains a beneficial tool rather than a replacement for human creativity and judgment. Transformers are playing a growing role in accelerating scientific research across multiple disciplines. In physics, they assist in analyzing complex datasets, such as those from particle physics experiments, identifying patterns that may lead to new discoveries. In chemistry, transformers aid in drug discovery, predicting molecular interactions and optimizing chemical synthesis. In biology, models like AlphaFold have revolutionized protein structure prediction, enabling breakthroughs in medical research. AI-powered simulations allow scientists to test hypotheses more efficiently, reducing the time and cost of experimentation. However, one of the key challenges in using AI for scientific research is trust. Scientists need to verify AI-generated results to ensure accuracy and reliability. Developing explainable AI models and integrating AI findings with human expertise is crucial for the responsible use of transformers in research. Cybersecurity is another field where transformers are proving to be valuable. AI-driven threat detection systems leverage transformers to analyze network traffic, identify suspicious patterns, and detect potential cyber threats in real time. In malware analysis, transformers help classify and detect malicious code by learning from vast repositories of threat signatures. Additionally, transformers assist in combating phishing attacks by analyzing email and text patterns to identify deceptive content. However, cybersecurity remains a cat-and-mouse game. Adversarial attacks, where malicious actors manipulate AI models, pose a significant risk. Researchers are working on making transformer-based cybersecurity models more robust against such attacks by improving adversarial defenses and anomaly detection techniques. Training large-scale transformer models requires enormous computational resources, leading to concerns about their environmental impact. Models like GPT-4 and PaLM-2 require thousands of GPUs or TPUs running for weeks, consuming vast amounts of electricity. The carbon footprint of these training processes can be significant, prompting discussions about the sustainability of AI development. To address this, researchers are exploring green AI initiatives, focusing on making transformers more energy efficient. Techniques such as model pruning, quantization, and efficient hardware utilization help reduce the computational burden. Companies are also investing in renewable energy-powered data centers to mitigate the environmental impact. The future of AI will likely involve balancing performance with sustainability, ensuring that AI advancements do not come at an excessive environmental cost. Transformers are driving personalization in AI applications, making digital experiences more tailored to individual users. In search engines and recommendation systems, transformers analyze user behavior and preferences to provide more relevant content. This is widely used in platforms like Google Search, Netflix, and Spotify. In education, transformers enable adaptive learning systems that adjust coursework and materials based on a student's progress and learning style. Personal assistants like Siri, Google Assistant, and Alexa are also becoming more context-aware, improving their ability to assist users effectively. However, AI-driven personalization raises ethical concerns, particularly regarding privacy and algorithmic biases. Excessive personalization can create echo chambers, reinforcing existing beliefs and limiting exposure to diverse perspectives. Striking a balance between personalization and ethical AI use is an ongoing challenge. Governments are increasingly exploring the use of transformers in policymaking and administrative processes. AI can analyze vast amounts of policy documents, economic reports, and public opinion data to assist in decision-making. In bureaucracy, transformers help automate routine tasks, such as document classification and processing applications, improving efficiency in government services. However, the use of AI in governance carries risks, including bias in policy recommendations and the potential for automated decision-making to lack human oversight. Ensuring transparency and accountability in AI-driven governance is critical. Policies must be designed to regulate AI use while ensuring that governments leverage AI ethically and effectively. Transformers are being integrated into space exploration efforts, enhancing capabilities in data analysis, navigation, and autonomous decision-making. One application is satellite image analysis, where transformers help process vast amounts of Earth observation data to monitor climate change, natural disasters, and planetary surfaces. Autonomous space probes, such as Mars rovers, benefit from transformer-based AI that enables real-time decision-making in remote environments. Another emerging area is natural language interfaces for astronauts, where AI-powered assistants provide mission-critical support through conversational interfaces. However, challenges remain. Deep space missions require AI systems that can operate reliably with limited computational resources and long communication delays. Future developments in AI efficiency will be crucial for supporting more autonomous and intelligent space exploration missions. One of the ongoing debates in AI research is whether transformers have fundamental theoretical limitations. While transformers have demonstrated exceptional performance in many domains, their ability to generalize beyond training data remains an open question. Unlike convolutional networks, which have built-in inductive biases for spatial hierarchies, transformers rely heavily on large-scale training to learn patterns. This raises concerns about whether they are genuinely learning abstract reasoning or simply memorizing statistical correlations. Some researchers argue that transformers lack compositionality, the ability to recombine learned components to solve novel problems, limiting their generalization capabilities. Others explore whether alternative architectures, such as recurrent neural networks, RNNs, with memory-augmented mechanisms, might offer advantages in certain contexts. Understanding these theoretical limits is crucial for the next generation of AI architectures. Scaling laws have been a driving force behind transformer advancements, showing that larger models generally perform better when provided with more data and compute power. Research by OpenAI and other institutions has demonstrated that performance improvements follow a predictable logarithmic trend. Doubling compute resources leads to consistent, but gradually diminishing, gains. However, scaling comes with challenges, massive computational costs, environmental impact, and data limitations. Some researchers argue that simply making models bigger is not the most efficient path forward. Alternative approaches, such as retrieval-augmented generation, ARGG, mixture of experts, MO, and neurosymbolic AI, aim to enhance efficiency without requiring exponential scaling. These strategies could provide a more sustainable and effective way to improve AI systems beyond current scaling paradigms. Transformers have a well-known limitation in handling long-range dependencies due to the quadratic complexity of self-attention. As sequence length increases, the computational and memory requirements become prohibitive, making it difficult for transformers to process long documents, extended conversations, or complex reasoning tasks. To address this, researchers have developed alternative attention mechanisms such as sparse attention, hierarchical attention, and linearized attention, which reduce computational costs while maintaining accuracy. Another approach involves incorporating memory structures, such as memory-augmented transformers and recurrent mechanisms, to allow models to retain contextual information over long sequences. These advancements are crucial for enabling more effective AI systems in domains like long-form text generation, code synthesis, and logical reasoning, where maintaining context over extended sequences is essential. One of the fundamental philosophical and technical debates in AI research is whether transformers understand language or merely perform sophisticated statistical imitation. Unlike humans, who develop abstract reasoning and conceptual understanding, transformers learn patterns from vast amounts of text without explicit symbolic reasoning. This limitation is evident in their struggles with tasks requiring deep logical inference, common sense reasoning, or causal understanding. Several benchmarks, such as the Winograd Schema Challenge and the ARC Reasoning Benchmark, aim to evaluate whether models exhibit true comprehension rather than memorization. One promising direction is hybrid AI, which combines transformers with rule-based reasoning systems, symbolic logic, or neurosymbolic architectures to enable more robust, interpretable, and intelligent behavior. The challenge remains, can AI ever achieve genuine understanding, or will it always be an approximation of human cognition? Inductive bias refers to the assumptions that a model makes to generalize beyond its training data. Traditional neural networks, such as CNNs and RNNs, incorporate strong inductive biases. CNNs assume local spatial hierarchies, while RNNs assume sequential dependencies. Transformers, however, are largely data-driven and rely less on explicit structural biases, learning patterns dynamically through massive datasets. While this flexibility enables high adaptability, it also raises concerns about inefficiencies and generalization limits. Transformers often require enormous data to learn meaningful representations, whereas models with strong inductive biases can generalize better with less training. One emerging research direction involves incorporating structured inductive biases, such as explicit syntactic parsing for language models or graph-based representations for knowledge reasoning, to enhance transformer efficiency and robustness. This hybrid approach could improve transformers' ability to reason about structured information and make more interpretable decisions. Training state-of-the-art transformer models requires immense computational resources, consuming vast amounts of electricity and contributing to carbon emissions. Studies have shown that training a single large-scale model can have a carbon footprint equivalent to multiple car lifetimes of emissions. This energy consumption stems from the high complexity of self-attention and the need for massive parallel computations. To address this, researchers are exploring efficiency improvements such as model pruning, quantization, and knowledge distillation. Additionally, green AI initiatives focus on optimizing hardware, improving training algorithms, and leveraging renewable energy sources for AI computation. These efforts aim to balance AI advancements with sustainability concerns, ensuring that future models remain both powerful and environmentally responsible. Transformers were initially developed for text processing, but have since been extended to multimodal learning, where models handle diverse data types such as images, audio, and video. Multimodal models, such as OpenAI's Clip, Google's Flamingo, and Meta's ImageBind, enable cross-domain understanding by learning shared representations between modalities. These models can interpret images based on textual descriptions, generate images from text prompts, and even analyze audio and video contextually. However, multimodal learning presents unique challenges, such as modality alignment, ensuring that textual and visual representations correspond meaningfully, and handling missing or noisy data across modalities. The future of multimodal AI involves building more cohesive and interactive AI systems capable of engaging in richer human-like reasoning across different data types, potentially paving the way for advanced AI assistants and creative AI applications. As transformer models scale, computational efficiency becomes a critical concern. One solution involves sparse architectures, where only a subset of the model's neurons or layers are activated for each input, reducing the total computation required. A prominent approach is the mixture of experts, MO, transformer, which partitions the model into specialized expert subnetworks. During inference, only a few experts are selectively activated based on the input, significantly reducing computational overhead while maintaining performance. MO models, such as Google's Switch Transformer and GLAM, achieve state-of-the-art results with fewer active parameters per forward pass. However, trade-offs exist. MO models can be harder to interpret, require careful load balancing across experts, and pose challenges in deployment due to their dynamic routing mechanisms. Despite these challenges, sparse and MO transformers represent a promising direction for making large-scale AI models more efficient and scalable. A significant limitation of transformer models is their inability to perform continual learning effectively. When exposed to new data, they often overwrite previously learned knowledge, a problem known as catastrophic forgetting. This makes it difficult for transformers to adapt incrementally without retraining on past data, which is computationally expensive. Several approaches aim to mitigate this issue. Memory replay stores and reuses old data during training to reinforce prior knowledge, similar to experience replay in reinforcement learning. Parameter isolation techniques selectively freeze parts of the model to prevent overwriting old knowledge. Meta-learning methods train models to adapt more efficiently to new tasks. Despite these advances, truly lifelong learning AI systems remain an open research challenge. The goal is to develop transformers that can learn continuously across different tasks without requiring excessive retraining, bringing AI closer to human-like adaptability. As powerful as transformers are, they are not necessarily the final step in AI evolution. Researchers are actively exploring new architectures that might surpass transformers in efficiency, interpretability, and reasoning ability. One promising direction is neurosymbolic AI, which combines neural networks with explicit symbolic reasoning to improve logical inference and decision-making. Another question is whether transformers alone can lead to general-purpose AI, AGI, an AI system with human-level adaptability across tasks. Current transformers remain data-hungry, struggle with reasoning, and lack common-sense understanding, indicating that additional advancements are needed. Finally, ethical considerations are paramount as AI continues to evolve. Issues such as bias, fairness, misinformation, and security risks must be carefully managed to ensure that transformer-based AI is developed responsibly. Looking forward, AI research will likely blend transformers with new paradigms to create more capable, efficient, and trustworthy systems. Thanks for watching. This concludes the day 3 of our course. Hope you enjoy it. For more tech courses and interview materials, please go to our website bowsy8.com.